lesson in Chem 1. This time we're going to be talking about something called colligative properties. That's how you pronounce that word, colligative properties. And these are relevant to us most springs as we're coming out of the winter, because these properties are the reason why we spread salt on the roads to keep the snow from freezing, to make the snow melt. So very important to us in a practical sense. But before we get to what they are, let's talk about the overall big picture of colligative properties. So colligative properties are properties of solution. So we're looking at the solution properties that depends only on the number of solute particles. Now, another way of talking about the number of solute particles is going to be the concentration. And so we'll talk about concentration and relate the colligative properties to the concentration of the solute in the solution. But here's something that's important. It does not depend on their identity. So it doesn't matter what the solute particles are. All it depends on is how many there are for a given solvent. And in the case of what we're talking about today, let me rewrite solvent. The solvent is going to be water. So in your book, I think it talks about 4 colligative properties. We're going to talk about the first 3 because they're the ones that are easiest to understand and the most relevant to what we do on a day-to-day basis. And those 3 properties are vapor pressure lowering, boiling point elevation, and freezing point depression. And pay attention to those words. Lowering means that the vapor pressure goes down. Boiling point elevation means the boiling point goes up. And freezing point depression means that the freezing point goes down. And this is all as the concentration goes up. Okay, so remember the directions of those arrows. Those are the effects that we're going to be talking about. So vapor pressure lowering is the first one. This is basically the one that gets the ball rolling when we're talking about these properties. So as you put more solute in, the solute lowers the vapor pressure of the solvent. Now, recall what vapor pressure was. Vapor pressure is when we have the solvent evaporating and condensing at the same rate. So what the solute does is it blocks the access of the solvent to the surface, and it prevents evaporation. It's basically slowing down that rate of evaporation. Okay, so as it slows down that rate of evaporation, the vapor pressure is going to go down. So as the concentration, why is that? The concentration goes up. The number of particles increases. The rate of evaporation decreases. So if you recall, the rate of evaporation and the rate of condensation were equal. So you don't need as high a pressure since the rate of evaporation decreases. So the vapor pressure also decreases. And think about that in terms of the effect. This is a higher effect. So the higher effect is a lower vapor pressure. So here's a diagram of exactly what's going on, a picture of what's going on in solution. So we've got on the left of this diagram, we have pure water. And pure water, we have the evaporation rate, we have the condensation rate, and the two of those should be equal. Now, what's going to happen is we're going to put some sugar. Sugar here is represented by this large purple sphere. It could be almost anything. And that large purple sphere is going to get in the way. So now we're blocking access here. So there are fewer molecules at the surface. So the rate of evaporation, let's see, we had 1, 2, 3, 4 going up, 1, 2, 3, 4 coming down on the left. Now we only have 1, 2, 3 going up. So we've decreased that rate of the evaporation. Because we've decreased the rate of the evaporation, so that solvent slows down the evaporation rate. So the rate of the evaporation goes down up here, and so the vapor pressure also goes down. So a higher concentration leads to a lower rate of evaporation, leads to a lower vapor pressure. Now, this vapor pressure then affects some other properties as well. And this blocking of the surface also affects some of the other properties. Now, what else happens at the surface is boiling. And so boiling point elevation is our next colligative property. And this diagram here is going to help us to understand it from a little bit more esoteric way of looking at it rather than just the molecular way of looking at it, a little more conceptual way. Boiling point elevation, BPE. So the boiling point is going up. Elevation, we're going up. As the concentration increases, so think about those particles blocking the surface. Because they're blocking the surface, it takes more energy to evaporate the solvent. So basically, let's scroll back up. What you're doing is you need to get more energy in, and change up. One of these days it's going to stop doing that on me. So to get more energy in, we're going to need more temperature. So let's use red for that. So we're going to have to get these molecules moving faster. And when they move faster, now we can get past that solute particle. And now we can get that rate of evaporation to go up again. Okay, so more energy, higher temperature, more energy. This is something that's important. It's higher temperature. Higher kinetic energy. Okay, so a higher temperature and higher temperature, like I said, higher kinetic energy, and the higher the concentration, the higher the boiling point. And that's the larger effect. Let me put that down here. Higher the boiling point is the larger effect. Now, what does this diagram to the right have to do with us? So this diagram is a phase diagram. I hope you remember phase diagrams, where we have our different regions of solid, liquid, and gas here. Now, when we do a solution, when we make a solution, this liquid becomes the solution. And this liquid is the only place where we've got solute present. So now, the pure solvent, so this would be pure H2O, is the red line here. And what happens, that was not supposed to happen, what happens with having a solute present, as we saw up above with the vapor pressure comes down. Okay, it's not liking me today. The vapor pressure comes down. So from that curve, we can draw arrows downward. This is the vapor pressure lowering. At all temperatures, that vapor pressure goes down. And so the solution, this green line, has a lower vapor pressure at every temperature. Now, as we get up towards the boiling point, here's the boiling point of the solvent. So this is a pure solvent. And if this was water, that would be 100 degrees Celsius right there, that dot that I just drew. Now, I'm going to change colors. Let's change to green. And let's blow this up a little bit. Let's blow this up a little bit to make it look a little easier to look at. So, as I get up towards the boiling point, notice that the vapor pressure at the original boiling point is now down. So this is no longer room pressure. This is no longer 1 atmosphere pressure. Here's our 1 atmosphere pressure line. So this is no longer the boiling point. Instead, we need to get to a point now where the pressure is equal to 1 atmosphere. The vapor pressure is equal to 1 atmosphere. And so what that means is that the temperature has to go up. This is a delta TB. The B is boiling. And so the boiling point of the solution is higher because you need more energy. You need to put more energy in to get up to that boiling point. Now, at the same time, look what's happening on the other end. And let's use purple over here. So at the other end, so not only does the vapor pressure go down at the original triple point. So here's our triple point of the solvent. But now the triple point slides down because it has to do with the interaction between the gas phase and the solid as well. So the triple point of the solution is down here. Because that triple point of the solution has moved down, what that means is that for every place along the solid liquid boundary, we have to move to the left. And what that does is it takes our freezing point of the solvent, again, the solvent was the pure solvent, and it lowers it. The delta TF goes down, and the freezing point of the solution is lower. So let's take a look. Let's write that out to the left, and then let's take a look at why that should be from a point of view of the actual particles that are involved. So let's scroll out so we can see everything. So freezing point depression, again, remember that means going down. The solute particles are preventing the solvent molecules from attaching to the solid. In other words, forming those intermolecular forces. We're trying to form those intermolecular bonds. Now, here's the thing. Because of that, this is the opposite now of boiling. More energy must be removed. Not added, but removed. Because, after all, this freezing is exothermic. So in order to freeze, you have to go to a lower temperature. So the freezing point goes down. The higher the concentration, the lower the freezing point. All right, so a bigger concentration is a bigger freezing point. So this is a larger effect. The lower the concentration, the higher the freezing point. And one of those kind of tricky questions that I might ask you about is this. The higher the freezing point, the lower the concentration. What this means is that the pure solvent has the highest freezing point. Okay, pure solvent has the highest freezing point. There's no effect. There's no freezing point depression to affect it. Okay, so we've seen it graphically. We've seen the words. Now let's take a look at the actual picture of what's going on. So on the left in this diagram, I have a picture of the structure of ice. And we talked about ice's structure before. Here are these nice big hexagons being held together by our hydrogen bonds. There's our hydrogen bond between the delta plus of the hydrogen, the delta minus, and all over we've got hydrogen bonds. All those hydrogen bonds forming these open hexagons. Hydrogen bonds are pretty strong, but here's our sodium chloride. So here's our chloride, and here's our sodium. It doesn't matter what we use as an example for the for the solute, this is going to work the same way. So what's going on is actually a couple of things. The water molecules are being attracted to the solvent, to the solute molecule. So they're being attracted. What that does is it gets in the way and it prevents them from being able to make those structures that they want to form the hydrogen bonds. So the solvent must push the solute out of the way. In order to do that, we need to remove more energy, because what that does is it makes the hydrogen bonds now strong enough. It's just like when you have intermolecular forces. The lower the intermolecular forces, the lower the temperature. Now we're getting that those intermolecular forces are strong enough to overcome those the kinetic energy and the other forces of the solvent, of the solute, that block them. And so removing more temperature makes a lower, removes more kinetic energy, and that's a lower freezing point. Now, this isn't just something we've made up. We have a couple of demos to show you what goes on. And these demos are going to be a video from Mrs. Glenn. And so I've attached that video to the assignment, and I want you to pause here, go watch Mrs. Glenn's video, and then you come back and we'll talk about what's going on. So hopefully you're coming back now from watching Mrs. Glenn's video and enjoyed her enthusiasm for the demos. Here's what we've got going on. The food coloring demo. In the food coloring demo, we started with a beaker, and here's my beaker on the right. And that beaker was full of water with a small amount of food coloring in it. All right, so water with food coloring. That food coloring is the solute. As it freezes, you have to realize that because the water goes in at room temperature, the freezing, it starts from the outside. That freezing starts on the outside and goes inward. So freezing water freezes from the outside in. And when it does so, what you end up with is pushing that solute out of the way in such a way now that the solute gets segregated. It gets pushed into the middle. And we see that solute, that food coloring, concentrated in the middle. And all around the outside here is pure water. And this is actually a way, if you do it the right way, you can actually purify materials by freezing them in such a way that you push the solute one direction and keep the pure solvent in the other direction. So the solid now, which was the solvent, the solid is now pure because it pushed the solute out of the way. So that was pretty cool to see. And then there's our club soda demonstration, the soda bottle. So let's describe what's going on in the club soda demonstration. So this is our before. Before we opened the club soda, the soda bottle was closed. Now, a couple of things were going on. The temperature was about -8 degrees Celsius, give or take. What that means is it's below the normal freezing point. But still a liquid. So it hasn't frozen yet. What's going on inside the bottle is that we have a high pressure of CO2 under the cap. And I may have mentioned this before, they actually keep that pressurized to about 5 atmospheres. A high pressure of CO2, what that means is a high concentration. Remember Henry's law, high concentration of CO2, and that leads to a freezing point depression and a low freezing point. So I'm going to draw a diagram off to the right here. And the diagram is going to have a couple of things on it. The first thing is going to be temperature. So here's my temperature scale. Here's 0 degrees C, and here's minus 8 degrees C. So here's where we are right now, at minus 8 degrees C. Oh, you know what? I got to put the minus 8 degrees C a little higher. Otherwise, this isn't going to work. So minus 8 degrees C. Now, let's change colors. And what I'm going to do now is put the freezing point. Here's my freezing point of the closed club soda. The freezing point is lower again because the concentration of the carbon dioxide is high. All right, so because the freezing point is lower, the temperature is greater than the freezing point, and so it's a liquid. So far, so good, I hope. Now, let's see what happens when we open the bottle. So we open the bottle. First thing that happens, the pressure of the CO2 goes down a lot. This is not just about the total pressure, like the 1 atmosphere that we have. This is about the pressure of the carbon dioxide itself. So it goes down a lot. It goes down to about 0.101 atmosphere. So it's really gone down by a large amount. So what happens when the pressure goes down is the concentration of the CO2 also goes down. What happens when the concentration of the CO2 goes down? The freezing point depression decreases. Now, a decreased freezing point depression means that the freezing point goes up. Right? Freezing point depression goes up when the concentration goes down. So on the right, what's happening now is the freezing point, the green arrow, comes up. Does it come up all the way to 0 degrees? I don't know. Does it matter? No, because now here's our freezing point of the open bottle. Oh, open, not open. Oh, what happened to my arrow? Okay, freezing point came up of my open bottle. Now, at the same time, the temperature is unchanged. We haven't had enough time to change the temperature. The temperature is still at negative 8 degrees Celsius. But now the freezing point the temperature is less than the freezing point. The temperature hasn't changed. It's the freezing points that changed. And because the temperature is less than the freezing point, it freezes. Now, what happened was, as it froze, let's do another color. Let's use our light blue. As the soda froze, it released heat. Because after all, freezing is an exothermic reaction. So it didn't freeze solid. Instead, we got that nice slush. Now, both of these experiments you can see or you can do in your own freezer. So for ice, if you look at ice, there are going to be bubbles in the middle of the ice. Those bubbles come from the dissolved air. There is air dissolved in the water, and so those bubbles form as the dissolved air comes out of solution. It gets pushed into the middle of the ice cube, and so that's why you see cloudy ice. It's air bubbles inside the ice. Likewise, with the club soda, you can do your own demo. So get your own club soda or your favorite carbonated beverage. It has to be carbonated. Put it in the freezer for maybe 10 to 15 minutes. And then crack it open, and you should see a similar effect. All right, so that's pretty cool. Your own kitchen science, if you care to do so. If you want to impress your mom or your little brother or sister, that might be a good way to do it. Sounds good? All right, so the homework is attached, and I will see you next time in class.